My name is Laura, and I'm an Ecosystems Management Technology student at Flemming College. Please welcome Julia Scarlett as she discusses soils with us.
So here we are in a pit. It's not your typical pit. It's probably much larger than any pit that you're going to dig. Here we can actually visualize what we're seeing a little bit better than you might get from a soil probe. Okay, so we've exposed a particular portion of the soil. It might be at a GPS unit. You might have compassed into a certain point and you're taking a soil sample where you would like to have a soil sample. And the next step is to identify what we can refer to as surface, subsurface, and parent material. And initially, what you can first see is probably the color differences. You'll be using the Munsell color charts to assess color based on hue, value, and chroma. And here we can kind of look at the profile as we see it based on, to a certain degree, initially, it's going to be a lot of color. Our profile, generally speaking, is the PDON, or based on a soil classification system of Canada, the Canadian Soil Classification System of Canada, where we're looking at being at least a meter in depth and a meter across. So if we were looking at the profile, we would want to expose it so that we have fresh surface soil approximately a meter across and also a meter down, or at least 25 centimeters past the obvious sea horizon. We know we've had some organic material. We see that we've got grasses and we've got some debris on the top. We wouldn't be classifying humic material or any organic material at this point because we don't have any growth. We also see that this surface, or this first layer, is quite dry. We've had quite a dry summer and a lot of the water does not get through because of the canopy that we have. What we've got is a zero line. So we've probably got a little bit of humic material that we can see that is accumulated, and that's going to show in that first layer. If we were to measure the organic component, or the litter, fermentation, and humic layer, okay, generally speaking, the litter and fermentation humic layer has to be at least 40 centimeters in depth before we can classify it as an organic layer. It is organic material, mind you. If we were to measure that material, we would be measuring up. So when we're talking about our profile and how we define our profile, when we're measuring the mineral soil, or combination of organic material and mineral soil, we would be measuring down from zero. If we were to measure the organic component, we would be measuring up from zero. Okay, so we might have a layer that's 35 centimeters thick on top of this material. So it depends on where you are. The more organic material will show up in areas where you have fens, bogs, swamps, riverine systems, where you're getting a real accumulation of material. And there's different profiles for Northern Ontario, Central Ontario, and Southern Ontario in terms of how we define an organic profile as well. So here we're pretty much looking at a mineral soil component, although this first layer we can designate as a layer where we can obviously see the darkness that's arising from some of the humic material that's accumulated over the years. In the particular pit that we're in, it has been historically a cultivated site, so we might give it another designation as being an AP layer, where we have plowed material or man-manipulated material. So again, the 0 point is, generally speaking, the interface between organic material and the inorganic component, those sands, silts, and clays that you've probably looked at in terms of particle size. Initially, what we can see is a really neat division. Now, this is dried soil. This is a little bit moister here, so you can see that moistness is going to affect the color as well. So this is dried, but the same coloration basically as the layer above it. When we first look at this profile, we can see a division here where we have darker color, and we can see a division probably to about here where we have some reddish material, but then we lose that color. Again, with the movement and the percolation of water going through the profile, it's going to change every profile that you see. When we get down a little bit further, we're actually starting to see a little bit of structure that's developing, in that we have something called the secondary structure, where we get material that clumps together and actually will form a shape, and eventually you would be defining this shape as angular blocky, subangular blocky, granular, or in some cases structureless, like you might have with some of the sands that we see in situ. So right away we can almost see an A layer okay, or this more of a surface type of material within the solum. This is probably the most weathered part of your actual profile. Then we get into what's referred to as a B layer, and the B layer is often referred to as being the diagnostic horizon. So when we have movement of material from the top of the profile downwards, okay, we can see the movement through an A layer. We can sometimes see parts of A layer going into B layer. We have chemical reactions which are going to show up as perhaps a whitening in the profile or a reddening in the profile when we have something like iron which oxidizes, or aluminum which shows as a layer of white throughout that profile. Once it gets to the B, we're starting to look at a little more depth of the profile. And so we often get material that is going to come to rest in that B horizon as well. So think of water moving down through your material and taking material with it. Okay? And this B horizon is kind of like where your house settles on its foundation. That you see layers, and it becomes a very telltale layer as to what order you might be looking at in terms of the soil profile. Once we get down to a C layer, okay, we can start to see some of that parent material. We might be able to hear it if you tap on coarse fragments. Again, with soil science, we're talking about soil material being 2 millimeters or less in terms of the size. Once we get into coarse fragments in this parent material, you can start to see and hear chunks of material as well. And this is the parent material. It's basically unweathered, so anything that's happening to the soil has usually transpired within that B horizon. Again, why it's a diagnostic horizon. So here we can see we've got one layer, and we're getting into the C layer as well. Okay. We also want to record things as we're looking at the profile. So we'd be recording color for this material, and any layers that you might have which are slightly different as well. Again, we can break these A, B's, and C's down a little bit further. You might have lenses of material that go through a layer, or something that's strange about a layer, which you would record as well. So we placed our measuring tape so we can measure that kind of change. Okay, so if we start at 0, we're going down, we're going in depth. So we can see that we have a horizon change at about 21, 22, 23, about 24 centimeters or so. Okay, and that would be our A layer from 0 to 24. Then our B layer would be from 24 to about 68. Okay, and our C layer would be from 68 to deeper than 120 centimeters. When we're recording these horizons, okay, we're also going to be classifying or using the distinctness of boundaries. Okay. So something like this boundary that we see, again, this is darker because of a little more moisture. The top part is quite dry at the moment. We can describe boundaries as being something that's fairly abrupt. So between this boundary and this boundary, we see a definite abrupt boundary where there's a distinct change, where we have less than 2 centimeters that we're seeing within change from one horizon to another. The more diffuse the boundary is, the harder it is to actually tell where the boundary is. So if you're finding it difficult to see the difference between one horizon and another, it could be because of horizon boundaryness and whether or not it's diffuse or very abrupt in terms of its transition. We're also looking at form when we're talking about horizon boundaries. So we might have a form that can be described as smooth, where your line goes right across your profile. We could have something that is quite wavy in some instances. Or you might have areas where you see that your boundary is kind of broken, where you have whole sections of one horizon going into another. Really not too evident here, but we can see some little pockets where that abrupt sort of boundary isn't as abrupt as we think it is, where we have a little more of a broken margin, where one transition zone doesn't seem to be as obvious as another. We can have irregular boundaries where we have material that has a really different shape to it. in terms of the form of the boundary. So you might run into across as many pits as you dig, you'll probably run into across combinations of many of these different distinctnesses and forms within a boundary. One of the things that we would be looking for if we're to designate an A horizon as having humic material in it is that we would have at least 17% of organic matter within that profile. There are lab tests where we can actually look for that. After a while, you'll get a feel of what your material is, and that's when you would actually do your finger assessment or textural analysis, is you'd be taking samples of each of these different horizons, okay, and bagging them and tagging them. Usually you're going to take a sample from within the boundary, somewhere in the middle. So I'll use this B horizon because the A horizon is quite dry. I would take a sample, okay, and I would have a bag on hand. And I would take enough of a sample that if I was going to process it for various things, I would make sure that I had enough sample to process something with. Again, you want your condition of your soil to be fairly moist. Okay, this could go back a little bit and eventually we might find some moist soil. You bag it, take a pen, and you would tag your bag as to what pit number you were in, and horizon C or B, horizon B, pit B, and to make sure that you had the appropriate information for your sample. That way you can take it back to the lab. You could actually do a sieve analysis to make sure that you're getting the particle size and diameters correct within your sample. You're also going to be required to take texture at a certain point. Okay? And taking texture again is often done in the field, okay, though it can be done in the lab. And you would go through a number of processes of doing a primary assessment or a finger assessment for texture. And you would find the texture for your A layer, your B layer, and your C layer. Often when you get into changes, you're going to find that there's quite a bit of change in texture. So when we start getting into this layer just above a lighter C, what we've got is a completely different texture than we have in the upper layers. We're starting to get into some clayey material, whereas the material above is quite sandy, a very fine sand. When we get to the moister bottom material, we can feel that there's already clay. And if you will have an exercise on finger assessment, on analysis of each of those samples. Again, representative sample. You wouldn't want to take your sample for your horizon B right where you see this transition line, okay, between the two textures. You want to make sure that you're taking the texture within that actual middle or sample where you've got something that's clearly defined. Sometimes in a soil sampling regime, you might want to either have a pit dug, as you'll see shortly, or you might be using something called a soil auger, or in some cases a soil probe. This is something called a split spoon auger, and as you can see, we're going to have our sample in this portion down here. Really sharp edges on here, and what we're going to be doing is basically getting about 6 inches of soil every time we're going down with the auger. We've laid out a tape measure here so that you can see when you're bringing up your soil sample, it's going to be a disturbed sample, and you want to try to keep it at the relative distances that you have with your soil auger. Okay? Basically, we're rotating through the first layers and putting a little pressure on it. It will give us a disturbed sample, but it does give us an idea of the soil that we have below the surface. We're getting down to the shoulder of the split spoon auger itself. And you can see how the material is coming up a little bit. That is a disturbed sample, and it's just something that we will be dealing with as we go. We want to make sure that the top of the auger is going to be at our 0 point. So we're at the interface of any of the organic material. Here we just have grass or sod, but in some instances you might have a forest ecosystem where you have an accumulation of organic material. Okay. So we want to get to the shoulder, a little bit lower, and then we're going to remove the soil auger, trying not to displace the sample too much. We want to remember that this is the top of our sample. So when we're actually measuring our soil sample, we're going to be measuring from 0 down. What we've got is the top of the split spoon auger. Okay, we're relating that to a 0 as we've got any kind of organic component above. So whenever we're dealing with a combination of potentially organic material and inorganic material, we want to make sure that we're measuring in the proper distance. You're gently going to be pushing out your sample, reminding yourself that you don't want to spread it out too much because you want as representative a sample as possible. When you dig in for the next 6 inches or so, we can kind of get an idea of where our 6 inches are if we sort of take a look at our flagging tape. And if we kind of move it down there, you can sometimes feel the top of your auger, depending on how large your hole is. And then you can get an estimate a little bit with your flagging tapes. I need to go just a little bit deeper than I have. A couple more turns. And then insert. Again, you want to make sure that you're remembering which is the bottom part of your sample, which is the top part of your sample. And then you're going to lay your sample adjacent to your first sample and gently sort of press the material out. You can see the shine when we get into some of the textural part of the clay. You actually see how the auger is basically done a shine test for you, and that surface has been flattened with the motion of the auger and the metal, and you can also almost see that it's a bit shiny because those flat particles have sort of aligned themselves with the pressure. You can see that we have a change in the texture. So when we're looking at textures, we've got something of a very fine sandy nature here, and then we actually get into this clay material. And when you get into things like the ribbon test and actually feeling for those textures, something to look for is the changes when you're actually augering the material as well. So you can see that this material is much more clayey than this material, which is much more sandy. You can also see change in color. And what we would do is we would record the changes in colors at the different depths that we have. So if we go up to our top layer again, we've got our 0 point, or the interface with the organic material, in our first layer of mineral soil. And what we have in this first 20 or so centimeters is the material that has moved down through percolation and infiltration of rain into those first layers of mineral soil, and that's how we're going to start defining some of our horizons. It's initially by the color that you see. In some pits you'll see a really obvious color change. Okay, that's really abrupt. Sometimes you might find a gradual change. Again, with a disturbed sample you might find some of that material showing you that you have a little bit more of a gradual change. You can cut that or look at that a little bit more and actually see if that's continuous throughout the core sample that you have, or if it's just incidental that you've sort of mixed some of your upper layers of soil with the lower layers of soil. You can definitely remark that there is a change here, probably a little bit of a gradual change, because we do have some of this darker mixture of organic material in our next sort of part of the profile. And going down, we have a lot of the same material. We've tried to overlap some of our augers samples so that we're actually trying to indicate 6 inches at a time, though you will notice that it does crumble at points and it won't always be a beautiful exact core because we're looking at a disturbed sample. And then once we start getting down to about a meter, we need to at least go 25 centimeters past what we think is the B layer and into the C. This little blue book, it's called the Munsell Soil Color Chart System, and it's used universally so that we could actually use a notation format of calling one color in Canada the very same color if we're halfway across the world. They use it in CSI when they're looking at dead bodies and the color of dead bodies as well. So we can kind of compare it to color chips. They usually do indicate that we have saturated soils, and they range from things like white to light grayish green. We have color chips on one side, and then we also have a description of the actual color itself, calling it things like dark greenish gray, very dark grayish green. Those would be for glade colors, which often indicate the saturated soils. The colors that we're using for more of our common soils are going to be ranging from the red color And what we call each page, or what we're referring to on each page, we give it a hue. And you'll find that the hue is recorded up in the top right hand corner of the page, and it gives us the general overall kind of color that we're dealing with. So in this case, we go from white, pinkish white, pale reds, weak reds, dusky reds, right down to dark reds. We have something along this axis which is called the value, and you'll see that the value is kind of like turning up the color. So we've got a reddish black at the bottom, and it goes to white when we get to a value of 8. Along the bottom axis, we have something that's referred to as chroma. Again, we have notations for each of these. So the chroma is going to show us the intensity of the color. So we go from a reddish gray on this side, okay, to something that is much more red over this side. When it comes to reporting that information, if we have a specific soil color, say we're picking this color, we can actually refer to the notation as being 10R 5/8, where we have the hue, the value, and the chroma recorded in a notation, which is worldwide in its usage. So we go from the general color, and what we want to do is, if we have a sample, and we'll use the sample right in front of us, say as our color that we're going to find, we want something that's going to have a similar hue to the pages that we have of color. So we're basically going to flip through until we find a page that we think. So what we've done is we flip through the pages to find the appropriate hue, that general overall background or color that we see. And now we're going to try to match it to something that is as close as we think. So our soil sample will go below the holes on the Munsell color chart. We have a piece of plastic on here. And what we're coming to is probably a match between one of these two. Again, you want to reduce the shadows a little bit so that you're not getting that intensity of light. In this case, we're probably looking at one of the closest matches as being an olive brown to this color. So therefore, we would have a hue of 2.5Y, a value that matches this color chip, so it'd be a 4, and then a chroma of 4 as well. And that's our color, is an olive brown. One of the first things that you're actually going to look at with soils is going to be the particle size diameter. It's used in a unified soil classification system. We also use it in a Canadian soil classification system. And one of the physical methods that we actually use to separate this is a series of sieves. Okay? The series of sieves goes from the largest opening, and our first sieve in this stack of sieves is actually going to be the cutoff. When we're looking at soils under the Canadian soil classification system, what we're looking at is material that is going to be smaller than 2 millimeters in diameter. Okay? Each of these soil sieves is going to represent a certain particle size, and this is going to later on relate to how water moves through soil, the plant availability of materials within the soil, nutrients within the soil, all relates to something that we're eventually going to classify as texture. Texture is based on these different sizes of particles, and when we're combining those, then we can later on use the textural triangle to figure out the percentages that we've calculated from a soil sample. Okay? So we start off with the largest sieve opening. These are brass sieves. Okay, and each of them will have a label that's going to identify the certain size diameter that we're looking at. Our first cutoff, we're trying to separate some of the coarse fragments. As a soil scientist, you're eventually going to look at the components that we have as soil, but we're also going to look at the components that we're going to call coarse fragments. So something you might know as gravel, or a boulder, or a cobble. In the sense of the true soil, we're actually not going to be classifying that component. We'll be using a bit of organic material, and at this point in the demonstration, we're showing you the inorganic material. So we have our stacked sieves, from the largest diameter opening to the very finest diameter opening, which literally you can't hardly see through. You can't even see the diameter openings on the smallest sieve. At the bottom, we're going to have a pan, and the pan is going to collect the finest materials. So in the bottom of the pan, we're going to have the silts and clays, which are the smallest particles. We have a known sample of our soil. We weighed the sample, and taking that weight, we're eventually going to be able to calculate the percentages that are retained on each of the sieves. Okay. We take our sample, and carefully we're going to be putting it in the top portion of the sieve. Okay. We don't want to make too much of a height, because some of the clays and the silts, if you're pouring this material too high up, they'll start to poof out, and you'll be able to start seeing some of the clays as we process our sample a little bit later. We want to make sure we have a lid on our stack, because we don't want the particles to come out of the sieve, because we want 100% of our sample. Because we're basing the percentages on weights, this is what we want to do, is we're eventually going to weigh each of these layers, and then we can transfer that into a textural characteristic. Now we're going to rock it. The base here is a rocker. Then we want to keep a couple of hands on our stacked sieve, and we're going to rock. Depending on the composition of our material, we're going to rock for anywhere between 5 and 7 minutes. Rocking for 7 minutes. Got a bit of a consistent rocking speed. What you want to do after you've finished rocking is to make sure that you leave it covered for approximately a minute. If you open the pan cover too quickly, what you're going to find is that you're going to have a poof of some of your silts and clay. And then what we want to do is just shake horizontally slightly, just in case some of the particles that aren't completely spherical, might be a little longer than they are wide. We'll go through that horizontally, just that last little bit of a check. Our first sieve is going to remove what we call the coarse particles. So when we're dealing with soils, the coarse particles are going to be larger than 2 millimeters in diameter. And this is eventually what we're going to be looking at in soils as being those large particles. And you can see it ranges anywhere from a gravel-sized particle to anything above 2 millimeters in diameter. If we were to use unified soil classification, some of this actually would be classified still as sands until we get up to about to 1/4 of an inch or 4.76 millimeters in diameter. And again, it's going to change how water flows through soil, how other material flows through soil as well. The next diameter that we have is giving us very coarse sand, and we're looking at particles that are smaller than 2 millimeters in diameter. What you'll start seeing is that we're getting into regular sizes of particles. Okay, so there's a little less of a range than we had with the coarse fragments. Okay, we're getting material that is kind of uniform in terms of its size. Okay, and depending on the mineralogy of the material, we're going to look at different colors as well. So sometimes you might see granitic colors that are quite pink, and we've got some quartz in there as well. So the coarse sand material, okay, again, we're looking at a range of particle sizes, but we have a uniformity to what's retained on the sieve. The material that's smaller actually passes through the sieve. We can do calculations with percent retained and percent passing to give us grain size analysis curves and different types of signatures that give us an idea of what's happening within the soil. The medium sand, again, going into uniform size. We're getting smaller and smaller in terms of defining the sands and the particles. Okay. We're getting to finer and finer material. You can start to see changes in how the material reacts when you're putting your finger through it as well. This is particularly used when we have a dry sample. It's something that you would normally send out for a lab analysis, or you can do a field lab analysis with the series of sieves. As we get smaller to the very fine sands, it's starting to look a bit floury and perhaps powdery, and you might see some of the clays that are still sticking to this. The last material that you have in the pan, these are the silts and clays. Okay, so we're looking at material that's smaller than the largest size opening on here. So in this case, we're looking at 0.053 millimeters, or about 53 microns. Okay. And these are the silts and the clays combined. And when we're doing some of our finger assessment methodology, what you're looking for is that material that's floury. Okay, so if you think about the flour in Mom's cupboard, okay, you can see how that material reacts quite similar to that floury material that you might have in your cupboard at home. Okay, and that's one of the tests that we'll look for, is how much percent of floury material you have within a sample. Once you've done the soil sieve, you have separated the sands, the silts, and the clays, and any of the coarse fragments that you have within a sample. Again, coarse fragments would be something that we actually don't consider to be soil when we're looking at the Canadian soil classification system, but we do have to record those coarse fragments. The silt and clay, because it's combined with the sieve samples, you have to do the hydrometer test to separate the silts and the clays. Once you have all those components, then you've got a weight of the material that you have. So the coarse fragments we would treat separately, but when we have sand, silt, and clay, then we can use the textural triangle to look at the percentages of sand, silt, and clay and give us a texture for that makeup. It's kind of like making a cake. If you have 15 eggs, a cup of sugar, and a cup of flour, it's going to give you something that tastes quite different than 5 cups of sugar, 1 egg, and 10 cups of flour. The same thing happens with soil. So we have a textural triangle which represents percent clay, percent silt, and percent sand within our sample. So we've calculated this based on the sieve analysis. We have 50% sand, 40% clay, and 10% silt. What we need to use is a straight edge. Okay? And generally speaking, we're going to start off with the highest percentage of material first. So in this case, we have 50% sand. We're going to align ourselves with the sand side of the triangle. Goes from 10%, 20, 30, 40, 50, 60, 70, 80, and 90 and 100% sand. Okay. This part of the triangle is 100% clay. This part of the triangle is 100% silt. Okay. So you have the lines to help you with this. What we want to find is 3 intersecting points. We know we have a 100% sample. We know the material that we've sieved out is within the proportions of 100%. Okay. So we start off with a 50% sand, okay, and you're going to just use your pencil, okay, to draw a line showing us where our percentage of sand is at 50%. Always keep your straight edge aligned with the little arrows where you have where it's applicable. Okay. The next value we have is 40% clay. We shift our straight edge. Okay. Along this axis, we're looking at clay sample, 10, 20, 30, 40, 50, 60, 70, 80, 90, and 100%. Okay. We move our straight edge to where we see the 40%. Okay. And now we only have to intersect this line. We have an intersecting line right here where we have the 3 points intersecting. This is again percentages based on sand, silt, and clay. This is where they're intersecting. This gives us a sandy clay. And that is the texture of a soil sample with 50% sand, 40% clay, and 10% silt. Occasionally you might be required to take the pH of a soil sample. Okay. With the simple pH test kit that we have, it's easily taken into the field. It's based on color comparison, so that we're actually looking for a development of color with a universal indicator solution. The universal indicator solution takes into account the extremes on the pH scale, and then we're basically going to look at color development of the solution above the soil. Very easy to do. You take your sample from your soil and you're going to fill the vial to the line that's marked number 1. So you're looking at maybe about 1 gram of soil or so. To about the 1 line, and then you're going to fill to the number 5 line with the pH indicator solution. Okay. The pH indicator solution will encompass the pH on the alkaline scale and also on the acidic scale. Okay. We would like to cover the end with a piece of plastic so that when we shake it, we might not actually be transferring the pH of our fingers to the pH of our sample. Okay. Often you will have a little stopper that you can put in. If you don't, just a piece of plastic, okay, and shake for approximately a minute. Once you've let your sample settle for approximately a minute, then you're going to use the color comparison chart. Okay. What you're doing is comparing the color development of the universal indicator solution with the color that you have that's developed in the vial. Okay. You want to hold it away from your card so that you have a little bit of light that passes between the vial and your color comparison. And then you're looking at the general overall hue of the color. So as you can see, this particular development of color is closer to the purple than it is to the blue. So in this case, we'd probably call that a pH of 8. If we were to look at the second vial, we're looking at, again, kind of a greenish development. If you've got a lot of clay in your sample, you might need to let the sample settle a little bit longer because the clays stay much longer in suspension. It's closest to the dark green, which would give us a pH value, again, a general pH of around a value of 6. One of the tests you might also be asked to perform in the field is a calcareousness test. This is to look for the free carbonates in the rock, as this might be a limiting factor to some species of trees growth or some species of vegetation growth. And it also indicates that we have those free carbonates that were probably on the limestone base of sorts. So when you have a soil that's taken from the shield area, what you're probably going to get is a reaction that is anywhere from something that's non-calcareous, where your hydrochloric acid does not react with the soil sample. You can see slight bubbling in there, so we're looking at probably something that's non-calcareous to a weakly calcareous material in this dish. As you play with your soils and gradually start to see the different soil types, what you're going to find is that you might change that you might see a different reaction in different soils. So here we can start to see a little bit more of a bubbling, and you will start to hear a little bit more of a hissing and cracking. Okay, so that we are in the intermediate stages where we could call something moderately calcareous, to a point where you might be looking at something which is in the ranges of strongly calcareous to extremely calcareous, of which we don't have a sample of. But something like this sample will probably show you that we're getting a lot more foaming that's occurring. We get a little thick foam. So in this case, we're probably looking at a range from something that's strongly calcareous to getting on the borderline very strongly calcareous. Okay, we don't have an extremely calcareous reaction, but if we mixed a bit of baking soda, and think about the volcanoes you made back in grade 5 and the vinegar and reactions you have with the baking soda, you're looking at something that's going to be extremely calcareous within that case.